Hi, this is Zeyong. Today I'll talk about our work titled Lattice Problems Beyond Polynomial Time. This is joint work with Divesh, Huck, Zvika, Sasha, Rajendra, Spencer, Noah, and Vinod. Without further ado, let's jumpstart to the definition of a lattice. A lattice is a discrete subgroup of Rn. Over here, I have a simple two-dimensional lattice. Usually, we specify a lattice by a set of basis vectors. So over here, we have a set of basis vectors b1 and b2 for this two-dimensional lattice. A lattice is then generated by taking all integer combinations of the basis vectors. If you recall, in linear algebra, we span the whole linear space by taking all linear combinations of the basis vectors. Now, if we restrict the coefficients to only integers, what we obtain becomes a lattice. Next, let's see what kind of lattice problems that we are interested in. In particular, we'll be talking about one of the most fundamental lattice problem, the shortest vector problem. Given a lattice, the shortest vector problem asks us for a shortest non-zero vector in the lattice. So again, in this two-dimensional lattice, the red vector v would be a shortest non-zero vector. So this vector would be a valid solution to the SVP instance. And typically, we use lambda1 to denote its length. With lambda1, we can then define the approximate version of SVP. So for gamma larger than 1, gamma being the approximation factor, gamma SVP asks us for a short lattice vector whose length is within gamma times lambda1. So for example here, gamma is taken to be 2, and any lattice vector within this green ball would be a valid solution for the corresponding gamma SVP instance. Next, the natural question to ask is that why do we study lattice? What's so special about lattice? And a very short answer to this is that it's an important candidate for post-quantum cryptography. In particular, last year, NIST, the US National Institute of Standards and Technology, announced 4 selected algorithms for post-quantum cryptography. And out of the 4 algorithms that's selected, 3 of them are lattice-based. So it does illustrate that lattice-based cryptography is a very promising candidate for post-quantum cryptography, for cryptography that's secured against a quantum computer. And one important feature about lattice-based cryptography is that we can have security guaranteed based on a worst case to average case reduction. In general, when we talk about a crypto system, we want it to be secure on average. More specifically, each time we run the crypto system, for example, we generate a new pair of public key and private key from some distribution. And we want to make sure that every time we run it, it is secure. As such, we want the problem to be hard for most of the instances. So over here, the average case problem that we are looking at is learning with error. And as it can be used to build a public key crypto system, the final goal we want is that we want to show that learning with error is hard for average instances. On the other hand, usually when we say that some problem is NP-hard, it suffices to show that it contains one hard instance. and it is much easier to show a worst case hardness than to show an average case hardness for some problem. But for lattice-based cryptography, we have this reduction from polynomial approximate SVP to learning with error, so that if we are happy to assume that, say, n to the k SVP is hard in the worst case, we are able to obtain the conclusion that learning with error is hard in the average case. Now, with that in mind, let's look at the complexity landscape for gamma SVP, measured in terms of the approximation factor gamma. So, on the left, we know that constant approximate SVP is NP hard under randomized reductions. Next, we know a co-AM protocol for deciding square root n over log n approximate SVP. Here, AM stands for the Arthur-Merlin game. And likewise, we have a co-NP protocol for deciding square root n SVP. These results are called hardness barriers because with these results, we do not hope to show that, for example, square root n SVP is NP hard. Because suppose that we are able to show that square root n SVP is NP hard, and we also know that it falls in co-NP, this will imply that NP is contained in co-NP. And as a result, this will collapse the polynomial hierarchy. Hence, we do not hope to be able to show that square root n SVP is NP hard. Next, we have a few worst case to average case reductions, and these are relevant to cryptography. For example, if we assume that n approximate SVP is hard, then we are able to show that the short integer solution problem is also hard. And making use of the short integer solution problem, we are able to build mini-crypt, or we are able to construct one-way function out of it. Similarly, if we are willing to assume that n to the 1.5 SVP is hard against, say, a quantum computer, then we have the conclusion that learning with error is also hard against a quantum computer. And as a result, we are able to build secured public key encryption. Lastly, for algorithm that runs in polynomial time, the best approximation factor that we can achieve is almost 2 to the n. So it shows that there is really limited things that we can do in polynomial time. Now, I have been talking a lot about hardness, some problem being hard, but exactly what kind of hardness are we looking at? There has been different notions or different assumptions of hardness being studied by people. For example, if we were to assume that P is not equal to NP, it is asserting that Z has no polynomial time algorithm. There are also stronger assumptions that people make. For example, the exponential time hypothesis. It asserts that 3Z has no sub-exponential time algorithm. There are even stronger ones. The strong exponential time hypothesis asserts that Z has no 2 to the 1 minus epsilon n time algorithm. And in our context, what is the hardness assumption that we are making for polynomial approximate SVP? Well, the common belief is that it is actually 2 to the Cn time hard for some not too small constant C. We don't actually have a proof for this. There are similar hardness barriers stopping us from showing this. But on the other hand, we do have a few evidence showing that it might indeed be the case. In particular, the best provable algorithm for solving n to the k SVP runs in 2 to the power of 0.5 over k times n time. So for constant k, think of k as being 1 or 2 or 3. This is 2 to the cn time for a not so small c. And the best heuristic algorithm also runs in 2 to the 0.29 over kn time. So again, this is 2 to the cn for some constant c. There are also works trying to show SETH hardness result for exact SVP in different LP norms. And with this evidence, we are happy to kind of assume that a polynomial approximate SVP is 2 to the cn time hard. And once we assume this, we can actually afford to run more time in the reduction from polynomial approximate SVP to learning with error. Even if we paid 2 to the epsilon n time in the reduction, we can still obtain a conclusion that learning with error is 2 to the c minus epsilon n time hard. And for c being a not so small constant, and epsilon we can choose it to be a very small constant, say 0.001. This gives a very significant result on the hardness guarantee for learning with error. And as we will see later on, we indeed obtain a stronger hardness guarantee as compared to the polynomial time reduction. Now this brings us to our results. Here are the known results that runs in polynomial time. The protocols on the left has polynomial size witness and polynomial time for verification. The worst case to average case reductions on the right also run in polynomial time. And what we did, we generalized these results to a world where everything is allowed to run in 2 to the epsilon n time. More importantly, we show that when we increase the running time to 2 to the epsilon n, the approximation factor of the corresponding gamma SVP problem improves by a factor of roughly square root n over log n. We also achieve a smooth trade-off between running time and the approximation factor when we substitute in different values for epsilon. It is also interesting to note that while the techniques that we use for different results are different, the final improvement in the approximation factor stays the same. Now, let's zoom in a bit and look at the individual results. On the left, we extend the co-AM protocol for deciding square root n over log n SVP to a co-AM protocol that decides constant approximate SVP when we are given 2 to the epsilon n time for verification and for communication. Likewise, we extend the co-NP protocol for deciding square root n SVP to a co-n time 2 to the epsilon n protocol that decides square root log n SVP. On top of this, we somewhat combine the two results, that is, the co-AM protocol and the co-NP protocol, and we obtain a new and simple co-MA protocol that decides constant approximate SVP and runs in 2 to the epsilon n time. One thing to note is that while all other results we have has analogs in the polynomial world, this co-MA protocol doesn't work directly in polynomial time, and we do not know how to make it work. As such, we leave it as an open problem. Similar to how the results above serve as hardness barriers for showing NP hardness of, say, square root n SVP, our results here serve as hardness barriers for showing fine-grained hardness result for SVP with small approximation factor. While most of the technical results happens here on the left-hand side when we play with the protocols, we realize that these results are applicable in the worst case to average case reductions on the right-hand side. As a result, we are able to apply them and port over the similar improvements in the approximation factor for these worst case to average case reductions. So previous works, the reductions that runs in polynomial time implies that one-way function exists if, say, order n SVP is hard, and public key encryption exists if order n to the 1.5 SVP is hard. Our work, on the other hand, shows that if we are happy to assume that square root n SVP is hard, then SIS is hard, and therefore we can construct one-way function out of it. Likewise, if we are happy to assume that n SVP is hard, then learning with error is also hard, and we can then build public key encryption system out of it. Hence, we strengthen the result in the sense that we are now assuming hardness on harder problems because the approximation factor is now smaller. One last comment that I would like to make is that in the 2 to the epsilon n time row, there seems to be no real distinction between a quantum reduction and a classical reduction, at least in the context of the worst case to average case reduction for learning with error. In the polynomial time row, there is an advantage of square root n in the approximation factor when one uses a quantum reduction. But such an advantage disappears when we are allowed 2 to the epsilon n time. Now, let me give you a concrete example on the improvements on hardness of the learning with error that we obtained. So we start with n to the k SVP, and suppose that we are happy to assume that this problem is 2 to the 1 over 10k times n time hard. So in the past, we know that n to the 1.5 SVP has a polynomial time reduction to learning with error. And for our result, we show that n approximate SVP has a reduction that runs in 2 to the 0.01 n time to learning with error. Now let's try to plug in the numbers. When we plug in k equals to 1.5, we know that this problem n to the 1.5 SVP is 2 to the 0.067 n time hard. Now with the polynomial time reduction, we obtain the conclusion that learning with error is also 2 to the 0.067 n hard. On the other hand, when we plug in the number for n SVP, we assume that it is 2 to the 0.1 n time hard. Now even after running a 2 to the 0.01 n time reduction, the conclusion that we can make for learning with error is that it is 2 to the 0.09 n time hard, which is much stronger than the conclusion that we obtained from the polynomial time reduction. Here is all I have for today. If you're interested in the technical details behind our proof, you may directly refer to the full version of our paper here. Thank you for your attention.